欢迎大家来到2023智源大会下午的环节。那相信经过上午The Kun 和 Max Tegmark 教授的精彩报告，大家都收获颇丰。那么下午的话，我们继续邀请到3位专家进行线上的特邀报告。他们分别是中国工程院院士、西安交通大学教授郑南宁，以及图灵奖得主、欧洲科学院院士Joseph Sifakis 以及Graphcore 联合创始人 CTO Simon Knowles。那同时的话呢，我们也邀请到CSDN 副总裁邹鑫和品玩的创始人骆一航作为我们的对话嘉宾。让我们有请图灵奖得主 Joseph Sifakis 来进行线上报告。他的演讲题目是 Testing System Intelligence。那同时的话，我们也请到了对话嘉宾 CSDN 副总裁邹鑫老师，有请。
好，今天非常高兴，也非常荣幸参加这个 BAI 的第5届大会。我是邹鑫，是 CSDN 的副总裁，也是一个码农，做软件开发有20多年的历史。今天很高兴来主持这个小小的这个技术分享。分享的嘉宾是这个 Joseph Sifakis 教授，他是各国科学院的院士，也是中科院的外籍院士。他也在我们这个深圳的南方科技大做这个杰出客座教授。他主要的研究领域是这个model testing。他因为在这个领域长期的和奠基性的研究，获得了2007年的图灵奖。那他在这个test model intelligence 这方面有很多的研究。我相信他的这个演讲会给大家带来很多的启发。好，下面呢有请这个 Joseph 教授，有请。
Okay. Can you hear me?
Yes.
Yes. Okay. So it's a pleasure to give this talk on testing system intelligence. And to start, I would like to say that there is currently a lot of confusion about what intelligence is and how it can be achieved. And this confusion is fueled by media and large technology companies that spread opinions suggesting that human-level AI is only a matter of years away. And we have also this mythology that has developed around the issue of ultra-intelligence, and some believe that machine learning is the end of the story. Of course, I don't share these opinions. If you open a dictionary, we will see that intelligence is defined as the ability to learn, understand, and think in a logical way about the world, and the ability to do this well. Machines can do impressive things, but machines cannot surpass humans in situational awareness, adaptation to challenges in their environment, and creative thinking. And I think it's very important to agree on a definition of intelligence. Without a clear idea about what intelligence is, we cannot develop a theory about how it works. I believe that today we have only weak AI that gives us the elements to build intelligence systems, but we have no principles and technique to synthesize them and to build a large intelligence systems as we'll build the bridges, for instance, of buildings from building blocks. And then for the future, I think that we will observe an accelerated convergence between ICT and AI that will lead to autonomous systems, and this will be a big step from weak AI to artificial general intelligence. You understand that autonomous systems support a paradigm of intelligence systems that goes beyond machine learning systems that are often specialized transformational systems. They emerge from the needs to further automate existing organizations by replacing humans with autonomous agents. This is envisioned by the Internet of Things. We talk about autonomous cars, smart grids, smart factories, and the autonomous systems are distributed systems of agents that are often critical and that should exhibit broad intelligence. They should manage dynamically changing sets of conflicting goals, cope with the uncertainty of unpredictable cyber-physical environment that, of course, collaborate harmoniously with humans agents. And I will explain that the realization of the autonomy vision is hampered by non-trusted AI systems that we have to use, and also by some difficult problems of systems engineering that are not so much related to agent intelligence. So this is an outline of my talk. I will try to compare human and machine intelligence to discuss this issue of trust of AI systems, introduce autonomous systems, and discuss about the future. Probably you know that Alan Turing, who is the founder of computer science, had the idea to compare human and machine intelligence with his famous test that is organized as follows. You have in two different rooms, a machine A and a human B, and an experimenter C that sends written questions to A and B and compares the answers. And Turing said that if C cannot tell which is the computer and which is the person, then A and B are equally intelligent. Why I'm mentioning this test? Because some people today claim that the system passed successfully the Turing test, so it's an intelligent system, as intelligent as humans. And this test has been criticized many times because success depends on human judgment, which is subjective, and the choice also of the test cases can introduce some bias. I can choose questions that favor a human or the machine. But another argument is that this test cannot be simply a conversation game. Much of human intelligence is expressed by interaction with the environment. We speak, we move, we exhibit social behavior. 2 years ago, I have proposed in a paper placement test. The idea is that an agent that can be a machine or a human is as intelligent as an agent B that performs a given task if A can successfully replace B. For instance, I will say that a machine is as intelligent as a human driver if it can successfully replace the driver. Or I will say that a human is as intelligent as a cleaning robot if it can successfully replace this robot. Note that the Turing test is a special case of this test where the task is just a conversation game. So this test relativizes, generalizes, and relativizes this concept of intelligence. Another way to compare human and machine intelligence is to consider the different types of knowledge humans and machines are developing and using. Probably you know that human thinking combines two systems, what we call fast thinking, that is non-conscious, automatic, effortless. This is the kind of thinking we use to handle all kind of empirical, implicit knowledge. When I walk, I speak, I play an instrument, my brain solves a very hard computational problem, but I don't know how. And system two is slow thinking that is conscious, controlled, effortful. And this is the source of any reason knowledge. When I program, for instance, I solve a problem, I think slowly, and I understand what I'm doing. And there is a striking analogy between these two systems of thinking and the two paradigms of computing we have today. We have traditional computers that execute algorithms that are written by thinking slowly and consciously. This is model-based knowledge. We can understand what we are doing, and this can be verified. On the contrary, neural networks generate empirical knowledge after training. This is data-based knowledge. They can distinguish cats from dogs exactly as kids do, but they cannot be verified. They cannot be verified because we don't understand how they behave. We have the problem of trainability, and this is a very important issue that I'm going to discuss later. Now, humans and machines handle, as I said, different types of knowledge, and this is explained in this diagram. We have so depending of different types of validity and generality. For instance, we have non-empirical knowledge that is independent of what happens in the external world. This is mathematical knowledge, or the knowledge we produce by reasoning. And below you have empirical knowledge about the world. The simplest kind is just events and conditions. Today, the temperature is 20 degrees Celsius, for instance. And then we have implicit empirical knowledge. This is system one knowledge for humans, and this is knowledge also produced by machine learning. We have prediction. We know how to. We know we solve some problems, but we don't know how. And above, you have scientific and technical knowledge that is empirical knowledge that is relies on mathematical models. And we have explanation, and we trust this kind of knowledge. So there is a big difference from a technical point of view between machine learning produced knowledge and scientific knowledge, and this is what I'm going to explain here, because the processes of development of knowledge are quite similar, because in both cases it's empirical knowledge. So here I'm considering an experiment in physics. So the famous experiment where Galileo noticed the proportionality between the force and acceleration and formulated his law. So you have three steps: experimental step, learning, generalization, just generalization, and explanation. Now, if you want to build a neural system that separates images of cats and dogs, say, you will start with an experimental phase where you will label the images you have a human that labels the images, and based on this labeling, you will train the neural network, and which hopefully will separate the images, but you don't have a model that explains this, and this is something very, very important to note. Now, another way to compare human and machine intelligence is to understand that humans are superior to machines regarding situation awareness. Probably you've seen this slide in the news, an autopilot that mistakes a moon for a yellow traffic light, and this would never happen to a human just because humans understand that traffic lights cannot be in the sky. So what is common sense knowledge? Common sense knowledge is a semantic model of the world that is built automatically since our birth, that it is enriched through everyday experience. And this is the model we use to interpret sensory information in natural language. What should we emphasize also is that human understanding combines bottom-up reasoning from sensor level to semantic model of the mind, and top-down reasoning from semantic model to perception. And let me give an example to illustrate this. Here, for instance, in this image, you recognize a stop sign partially covered with snow. Why? Because the sensory information is connected to a semantic model, a conceptual model that you have in your mind of the stop sign with its properties, the size, the color, vertical position, etc. In contrast, the neural networks must be trained to recognize stop signs in all possible weather conditions, and this is a very, very important difference. Or if I show you, for instance, this sequence of images, you instantaneously interpret it as an aircraft accident. In contrast, the machine can analyze each frame separately, but is not able to connect causally what happens in each frame to reach the same conclusion. So, summarize, for machines to match human situational awareness, they should be able to build a model of the external environment and understanding particularly entirely new situations, and to combine learning and reasoning. And this is a very hard problem. It's probably the most difficult problem to solve for AI today. And I'm not optimistic about the possibility to solve this problem in the near future, at least as shown by the poor progress we made so far in the semantic analysis of natural languages. A very important question here when you test the intelligence of systems is how to validate the properties. And I said that an important issue is the non-explainability of AI systems. So let me give a precise definition of what we need today. A system is explainable if its behavior can be described by a mathematical model or a model we can understand. And one way to do that for neural networks is to build compositionally to compute a function that mathematical function. Theoretically, this is possible. In particular for feed-forward networks, because we know the functions computed by each node. So this is the weighted sum of inputs where we apply some activation function. So in principle, theoretically, should be possible, and there are papers that deal with that, to build this function. But you understand that complexity limitations do not allow this. Now, if we want to validate system properties, there are two ways. There are two methods, or validation methods. One is verification, and verification is made by reasoning on a model. So verification is not applicable to neural networks in particular. And verification is very important in modern systems engineering. Why? Because you need verification to guarantee universally quantified properties like safety or security, because you have to explore all the possible states of the system to guarantee this. And so for AI systems, the only way to go is by testing, and testing is an empirical validation method. You have limitations, obvious limitations, the kind of properties you can validate, but also you cannot have the kind of guarantees you have from verification. Properties, universally quantified properties can only be falsified. So this is a serious limitation. And okay, let me also say that systems engineering focuses on three main types of properties. So any requirement can be decomposed into three different types of properties. Safety properties, meaning that the system during its execution will never reach bad states, so dangerous states. Security properties, that mean that the system is resilient to attacks. And performance properties also are very important because they characterize technical and economical criteria concerning resources and their exploitation. Now, it's important to say that today we see in publications, some publications that claim that intelligent systems satisfy some properties without being rigorous enough. In fact, epistemic and methodological imperatives demand that assertions that a system satisfies a property be accompanied by a rigorous definition. So, for instance, if I say my system is honest, then you should give a definition of honesty and also an associated validation method. So typically, for instance, you can read that some company has driven 10 billion autonomous miles in simulation, so the autopilot is safe enough. But this argument is not technically defensive just because they don't say how simulated miles are related to real miles. Or people talk about a responsible AI, which implies that AI means criteria like fairness, reliability, etc. But you should provide, of course, the characterization of these properties and say what it means for a neural network to satisfy these, to check these properties. And of course, there are even papers that talk about AI alignment, which means that we will align a conversational agent with human values, but we don't even understand how human volition emerges and how all the process that is value-based decision process of humans. So I think that there is a danger here because people claim that intelligent systems satisfy properties and don't follow a rigorous approach. Let me say a few words about testing. This is very old stuff, but so what it means to test a system S that has inputs X and produce output Y. So the properties will be a relation between input and output. I have the system, I have the property, and you will have an ORAC. What in technical terms is called an ORAC. That is an agent that when you apply X, you observe Y, will say success or not, pass or fail. So the ORAC is an agent that will evaluate this predicate and decide. Now, if I say that S satisfies a property P, and I want to validate this, means that for any possible input X and corresponding Y, this property is satisfied. And you understand that this is, I mean, for systems with a large number of inputs, this is impossible. I mean, we should have a method to cope with the complexity. And for this, I'm not going to the details. Test methods have been successfully applied to test hardware or software, or in physics, we apply test methods, or in medicine, we apply test methods. What characterizes a test method? The test methods provides criteria to choose among possible test cases here and evaluate the results. So a test method is characterized, in fact, by an efficiency function. The efficiency functions will characterize the efficiency of a set of inputs, capital X, that measures the extent to which this set explores the characteristics of the system behavior in relation to the property we want to validate. And then a score function that will produce a score, so the likelihood that S meets P for a set capital X of inputs and the corresponding Y. Without giving details, in order to have such a theory, we don't have such a theory for intelligent systems. I can explain why. Another strong requirement is reproducibility. Reproducibility means that the results of a test campaign are independent of the choice of the inputs. So if, for instance, two sets of input vectors here for the system have the same efficiency, then the results, the score will be more or less the same. And this guarantees the objectivity of the result. In fact, you show that all depends on how deeply you explore the system that you test. Now, just to provide a comparison and the application of this idea of testing for the various kinds of systems. So here I have a system in physics or a flight controller have worked on that, or that has to meet strong safety properties. Here we have what we call white testing, because we have a model of the system, so we can explore all the possible states of the system experimentally and reach what we call conclusive evidence in some standard. And then this is a case of statistical testing. So here you don't have a model of the system, but you have some theory, for instance, to evaluate the efficiency of a vaccine, and you can reach some statistical evidence. And here I'm considering three different types of intelligent systems: an image classifier, a self-driving car system simulated, and the ChatGPT. So you see, for these two systems, the property can be formalized. We can have oracle, so here a human oracle, here this can be automated. In fact, I'm working on this problem. And here, of course, we need some theory. A theory that will define some coverage criteria, some efficiency criteria, and we don't have. And of course, for ChatGPT, nothing is possible. Why? Because we cannot formalize the question-answer relation, and also, okay, the oracle will be a human, and it will apply subjective criteria. Where you see here, you can have a human oracle, but the criteria are non-ambiguous. Now, without giving details, I will say that for intelligent systems, we are limited, because the properties should be rigorously specified, and this excludes all the language transformers, and also should be observed, and so this excludes what we call human-centric properties like intentionality, belief awareness. And also there are other problems I don't have time to discuss, but we have problems due to the fact that you can have adversarial exams for neural networks. And this comes at odds with the requirement for reproducibility. I don't have time to discuss. Adversarial exam means that observationally equivalent test cases can give different scores. Now, let's talk about autonomous systems, because I said that autonomous systems are an important step toward artificial general intelligence. At first, let me explain the difference between autonomous and automated systems. I'm considering here 5 different types of systems that interact with their environment. And for this, they need the situation awareness and decision-making mechanisms. So for the thermostat and the shuttle, problem is very simple. Situation awareness just reading values from the environment, and the control is static here. You can design a control, it's easy. Things become much more complicated for a chess robot, not so much for situation awareness, but you know that we need dynamic planning of goals because we have this explosion of all the possible configurations and moves of the pawns on a board. And then things become much harder even for football robot, because players should understand, analyze dynamic images, and also choose between deal with dynamic goals, and these are very hard problems that become harder even for autonomous cars. So let me try to characterize the behavior of an autonomous agent. I have proposed in a paper 5 years ago this architecture, and I have tried to apply these ideas to self-driving cars. So here I'm considering the autopilot of a self-driving car. So this is a system that interacts with an environment in the obvious manner. You have sensors and actuators. So you receive frames here. To achieve situational awareness, you will have a perception function that will analyze the frames, will identify obstacles, and then their kinematic attributes. And this reflection function will build a model of the external world based on which you make decisions. And you make decisions by combining two functions, goal management, and for each goal you can start planners, and the planners will generate commands sent to actuators. Now, it should be emphasized that for autonomous agents, you can have many different types of goals. For self-driving cars, more than 15 different types of goals. Short-term goals, avoiding collision or keeping the car on a trajectory, or long-term goals, I'm here and I'm driving to a destination. So the problem is very hard to solve. So this regarding the reactive behavior of this agent, but also it's important to emphasize that autonomous agents should exhibit proactive behavior based on the management of knowledge. So you see here I have a component. It's a knowledge repository where I can have pre-stored knowledge about, for instance, the properties of the objects I can encounter. And also I have this self-learning function that monitors information here and updates regularly this repository. The idea is that you can use knowledge for enhanced prediction and decision-making. Let me explain how. So if in a self-driving car, I have, say, in front of me a truck, and the perception function identifies the type of truck, and I have pre-stored the properties of a truck, I can predict, I can know, for instance, maximal acceleration, maximal speed, so to have better prediction here, or the self-learning function can estimate some parameters I'm using for decision-making. So this is the way I have imagined the architecture of an autonomous agent. I should say that I don't know how to implement according to this principle autonomous agents because of many complexity limitations. Complexity of perception, this is well understood, to cope with ambiguity and vagueness of environments, complexity of uncertainty, because you can have dynamic changes in the environment caused by physical and human processes that are unpredictable, and then the complexity of decision. I said that for self-driving cars, you can have to deal with more than 15 different goals, and these goals are subject to different timing constraints. So if I cancel a goal, if I change a goal, if I delete a goal, this change should be consistent with all the goals I am pursuing, and these are very hard problems, technically speaking. What I would like also to explain that it's not enough to design an agent. You have to integrate it in a complex cyber-physical environment. If I have a self-driving platform, for instance, for a car. But also agents should be able to harmoniously collaborate with human operators. And we know the problems. This is not just a simple human-machine interaction problems, and we know setbacks of autonomous car industry in trying to solve these problems. Now, if you have many agents, then the problem of their coordination appears, and you have to face this problem. And it's important that the coordination of agents does not impede the achievement of their individual goals. And also the agents synergize, collaborate to achieve global system goals by demonstrating what I call collective intelligence. So typically, for instance, for self-driving systems, the cars should coordinate to avoid the bottlenecks or to have a better occupation, the best possible occupation of roads. Okay, so what we are standing today in this challenge of building autonomous agents. We have, on the other hand, very well developed methodologies for automated systems that guarantee their trustworthiness, and these are model-based. So these methodologies are defeated by the complexity of autonomous systems, and also because of the fact that we have to consider to integrate neural networks. Now, another way that has been taken by some big tech companies is to build end-to-end self-driving solutions enabled by AI. So to integrate, for instance, to have self-driving platforms where you have a huge neural network that are trained mainly by simulation. You apply, say here, you analyze frames, you receive frames, and you produce steering angle and braking signal. Such platforms exist. I would not recommend that you use them to drive cars because of their lack of trustworthiness. And there is also another very, very important problem that people don't talk about is the problem of the integration of these platforms in electromechanical systems. Current techniques do not scale up and are not applicable to monolithic neural networks. So I think that for the future, we should strive to take the best from each approach and integrate in the same architecture model-based and data-based components. For instance, we have very good algorithms for decision-making. This can be so model-based components. And on the other hand, we can use, we need to use neural networks for perception, to solve some hard optimization problems. And of course, the deployment problem remains open. Now, this is my view about how far we are now from reaching this autonomy vision. Here I'm considering this diagram where this figure where I have one act. I consider that intelligence is characterized by situation awareness and the ability of decision making. So I have a situation awareness for single domain or many domain are restricted situation awareness here, decision making for a single agent or for a system of agents. And I think that the focus of AI is currently this. And what we try to do with self-driving cars or other autonomous systems is this, because you will have goals that will be multi-domain. And of course, in the future, we should strive to build systems. And I talked about the problem of a sound integration of agents and okay, so building self-driving systems that exhibit collective intelligence. So my opinion is that there is a long way to go. I don't have time to comment to say more on this. Now, let me try to conclude by showing 3 slides about the future. I think that in the future, it will be important to integrate AI techniques in traditional systems engineering. This is because we need to have intelligent artifacts in general. And it's important also to say that traditional systems engineering today is disrupted somehow by new trends that contradict the well-established practice, especially for critical systems engineering. Some industry that they don't follow this concept of security by design, as I said. For instance, they adopt end-to-end solutions that are based on AI. In some countries they allow self-certification. For instance, the United States, which means that not the manufacturer, not any independent institution will guarantee the trustworthiness of the system, but the manufacturer. And this is a bit strange. And then also they allow some regular updates of critical software. You know this, and this is at odds with critical systems engineering practices. Now, in the future, we have 2 important work directions. One is hybrid design of intelligent systems, where we should be able to integrate AI components in traditional systems engineering development methodologies. Of course, AI will remain non-explainable for probably forever. So we should devise techniques for building trusted systems from untrusted components. We know how to do that for hardware systems. We have to develop theory for that. And also system validation is marked, as I explained, by the shift from verification to testing. I think that for intelligent systems, the best we can expect is statistics-based techniques to estimate confidence levels. We should be satisfied with weaker transconfidence guarantees. We will never have the transconfidence guarantees we have for traditional systems. For instance, for critical systems, we require 10 to the minus 9 failures, less than 10 minus to the 9 failures per hour of operation. This is not achievable. And then to summarize, I think that to bridge the gap between automation and autonomy, there is a long way to go. This is what we knew also from self-driving cars. The transition cannot be progressive. And to reach the full autonomy vision, we need to develop, in my opinion, new scientific and engineering foundation. This will take some time. The other important issue is the issue of intelligence. We should agree on a concept of intelligence. The replacement test relativizes, as I said, and generalizes the concept of intelligence. So one idea is that there are multiple intelligences. Depending on the task you choose, and this will require specific skills, and this defines a certain type of intelligence. And also we can consider tasks that do not operate that operate, for instance, in virtual environments. So, for instance, you can have compare the intelligence of a human and a machine playing a game in the metaverse. Okay, and then, of course, if human intelligence is the reference, is the benchmark, artificial general intelligence should be able to perform and coordinate a set of tasks that characterize human skills. This seems very important. Something else, an idea I like is this idea of the space of possible intelligences. Why? Because humans are limited in analysis of multidimensional data. We know this. And AI systems outperform humans in learning multidimensional data. On the contrary, humans are capable of common sense, knowledge, abstraction, creativity, etc. So in this figure here, I show this complementarity, and in fact, we can imagine that by combining these skills, we can have somebody that has an agent that has this intelligence, okay, that is the extreme intelligence for humans and machines. Another idea that I find interesting is that the replacement test shows that equivalent systems may have very different creative processes. And this is an idea that should be further explored. For instance, a problem I can solve symbolically, perhaps I can solve it also by using machine learning. And in fact, there are some interesting results today that show that LLMs can solve problems that we have solved by using symbolic reasoning. Here I'm given the name of a tool that does this. So for the future, it's very important to explore this vast space of intelligences, and particularly to understand how human symbolic intelligence is related to machine intelligence. Now, my last slide. I think that validation of intelligent systems will be a very, very hot topic in the future. I have already commented on this tendency to ignore the limitations of validating intelligent systems according to established criteria. That criteria that are methodological and epistemic criteria. So you can read, for instance, that LLMs understand natural language. Okay, I don't think that this is an acceptable argument. I mean, technically speaking. And also, you can find papers that attribute mental attitudes to systems like belief, desire, and intention. And I found this sentence in a paper that I think it's interesting to read it. We cannot show that an agent always does the right thing, but only that its actions are taken for the right reason. I think that this is a bad approach. This means that you see, if somebody, if a human does something bad, you examine also the motives, okay, the reasons. But I think that this is a bad approach. I mean, from a technical point of view, because it assumes that machines can understand the world, and we know since the Chinese room argument that this is not possible. Of course, there is a problem that if we apply strict systems engineering criteria, we exclude, for instance, language transformers, because we cannot apply rigorous testing techniques. So one question that arises is whether we can apply, for instance, qualification exams to LLMs. And probably LLMs will be able to pass the final exams in some field as students do. However, I would like to here say that there are two fundamental differences between neural networks and humans. Human thinking is robust. So if a human is sane, his thinking is robust. And while neural networks are not robust, slight changes in questions may imply very different answers. And also, human thinking is based on common sense knowledge and is better placed to avoid inconsistencies. And we know that LLMs can produce very, very inconsistent answers in some cases. So just to conclude, I think that we should admit the need for rigorous validation methods for intelligent systems and strive to overcome current limitations with clarity, okay, without cheating, and to develop new foundations. And if possible, we will revise epistemic and methodological requirements, but being careful about that and understanding what we are doing. So on this, I would like to thank you for your attention and say that in a book I have published 1 year ago, I discussed many of these issues. Thank you very much. Thank you.
Thank
Hello?
you very much. Yeah, thank you
Yes.
very much for this insightful talk, Professor Joseph. May I have a couple of questions?
Yes, of course.
Yeah, in the self-learning part of the AI, you mentioned that
Yes.
even the advanced algorithm like Tesla might mistake the moon from a yellow traffic light, right?
Yes.
And so for a human being, I mean, human being also make mistakes. But once a human realizes that's a mistake, he or she can correct it and then proceed. And
Yes.
how can an algorithm to learn and then get better without being reset by its manufacturer or completely retrained? Like, can it learn on the go, right? How can we implement such self-learning, self-correcting mechanism in a autonomous system?
Well, I mean, the obvious answer here is that if for instance, for autonomous cars, if you want to have some guarantees, that you use redundancy. I think that the problem with neural networks is that they cannot contextualize the information, and humans contextualize the information. You receive sensory information and you put it in a context. So this contextualization, we don't have it for neural networks. And there is a technical problem. I'm working on self-driving car. And the technical problem is the following, very, very precise technical problem I am facing. You receive sensory information from cameras. So you would like to combine this sensory information with information from maps. And the information from maps is symbolic. So you can have high definition maps in some library and say, oh, I would like to match this. and you will have better guarantees because you will not rely only on cameras, and also you can have better predictability. I don't know how to solve this problem. Okay. So it's as simple as that. There is a gap today between concrete knowledge that is produced by neural networks and symbolic, and this is the gap also in AI between symbolic AI and connectionist AI. I mean, this is an old problem, okay, and we don't know how to bridge that. It would be fine. I mean, it would be excellent if we can combine the two approaches, but we don't know how. And the human mind has this ability to connect sensory information to a conceptual model of the world. If we do that, then we can reach human intelligence.
Yeah, another similar question. It's about when there are rules, for example, in car driving in England and France, they are different. Cars are driving on different sides of the road.
Yes.
So if one human driver drive from England to France, he or she can adjust it automatically. So how can we instill, how can we teach the algorithm such rule, right? Or it can learn on the fly. So is there a way to trigger the different set of common sense? For example, in England, this is common sense. In France,
yes, okay, yes. This is exactly the issue of contextualization. I change context, and with the same system, you would like to be able to drive the car. Okay, so if I have to retrain my system when it moves from France to okay, I mean, this is the issue of contextualization. I agree. Yes.
Okay. My last question. At the end of the slide, you mentioned that we need to improve our testing or our criteria to judge whether or not a model is really good.
Yes.
From the current data, let's also take auto driving, for example. Compared to average human being, I think the auto driving algorithm is already surpassing in terms of correctness. But it seems to me that the society has a expectation of our auto driving algorithm to be perfect. If you ever make a mistake, well, that's a big problem.
Yes, that's true. That's true. That humans judge more severely machines than if a human has an accident, a human can explain why this happened, and people are ready to hear this. On the contrary, if a machine has an accident, of course, okay, it's very different. So this is this is a criteria. But on the other hand, I think that what happens with humans is more acceptable also because, I mean, we're familiar with the way of thinking of humans, while machines can have some unpredictable behavior, okay? That can be considered as completely crazy, okay? And this is, there are such phenomena, like, for instance, the anomalies that we know for neural networks, okay? So it's, yes, you have very, very different behaviors, okay? Yes.
Actually, we got one more question from the audience. Many of our attendees are college students right now. So when they see the AI making progress every week right now, right? So they are replacing coding work and then other tasks. So they wonder, in today's world, if I am in an IT-related major in college, should I still learn basic, for example, sorting, logic, or should I leave that to algorithm? So what is the kind of a career path for today's computer science or IT major? Do you have any advice for them? Thank you.
Yes, but you see, I consider that IT is more like a technology. If you want to train, an AI, okay, you will use algorithms. You will write the programs. You will write algorithms, okay. Perhaps for AI you need some more special mathematics, but I'm considering that AI is part of computer science that evolves. It's very important for students to understand the basics, of course, the theory, to have a strong background in mathematics. And I don't think that this is an important dilemma. students should have a broad culture and also understand all the systems engineering issues that will appear, okay? Because AI will be married with systems engineering. That's very important.
Okay, thank you for your advice. That's about time. So thank you very much, Professor Joseph Sifakis. And
thank you for inviting me. Thank you.
Thank you. And we hope we can sometime meet face-to-face in China, and then we can discuss more.
I will start traveling to China this year. Yes.
All
okay.
Right.
Thank you.
Great.
Bye,
Looking forward to meeting you.
Thank
All right.
you.
Bye. Thank you.
Bye everybody.
好，谢谢。上面就是我们跟这个 Joseph 教授的这个演讲和讨论啊，谢谢大家。
OK， 那十分感谢两位老师的精彩对话。那下一个环节，我们即将有请 Graphcore 联合创始人 CTO Simon Knowles， 给出线上的报告，报告题目为 Matching Silicon to AI Algorithms。那么我们很有幸的请到品玩创始人骆一航老师作为这个环节的对话嘉宾，有请。
嗨，大家好。我今天非常高兴能够来主持今天下午的这个环节。今天我们下午是一个跟Graphcore 的联合创始人和 CTO Simon Knowles 对话的这样的一个环节。我先用中文简单的介绍一下我自己，然后我再用英文介绍一下 Simon， 然后请 Simon 做他的演讲哈。我是骆一航，是科技媒体品玩的创始人哈。品玩是一家这个中国比较领先的这样的一个中英文双语的科技媒体，然后我们同时在北京、上海、深圳、杭州，然后新加坡和旧金山都有办公室。我们关注中国科技创新的全球化和全球最前沿科技上创新与中国的交流啊，这个是我本人的这样的一个情况。And today is my honor to be here hosting the online report given by Simon Knowles. So Simon Knowles is a co-founder, CTO, and the EVP of engineering at Graphcore. He's recognized as the original architect of the Intelligence Processing Unit, the so-called IPU. So with a career spanning over 30 years, Mr. Knowles has been designing original processors for emerging workloads with a focus on intelligence since 2012. And then prior to Graphcore, Simon co-founded 2 other successful processor companies. The first one, Element 14, was acquired by Broadcom in 2000, and the second one, ISRA, was acquired by NVIDIA in 2011. Simon's educational background includes an electrical engineering degree from Cambridge University. So I'm now thrilled to welcome Mr. Simon Knowles to give us the academic report with the theme, Matching Silicon to AI Algorithms. Okay, welcome, Simon.
Thank you, Thomas. Thanks for the invitation to talk at this prestigious event. Can you all see the screen that I am sharing? Can you see that, Thomas? Yeah.
Okay.
Okay, good. So I am not as much of an expert in AI as most of the people on this call. So I will probably not teach you anything about AI algorithms, but I hope to be able to illuminate at least something about chip design for AI, and perhaps tell you something about the intersection of those two and how we might be able to get chip designers and AI algorithm designers to work together for a better AI outcome in future.
Okay, that'd be great.
Okay, right. So where are we with AI? Research, a lot of research over many years has got to the point where it has delivered clearly potent AI with general utility. Investment now pivots from the discovery of what AI can do, the capability phase, to the deployment of AI, which is efficiency focused. And chips are adapting accordingly. Deploying AI today is expensive. Training models is expensive, and deploying them in inference is expensive. So what can we do about that? The principal resources that an AI processor has for the execution of any algorithm, but in particular AI in this case, are as follows. Matrix arithmetic, obviously, which is calibrated in flops per second at a certain energy per flop, floating point operation. The memory capacity, and for those unfamiliar with silicon, memory doesn't cost any power at all while it's just remembering things. It only costs power whilst you're accessing it, reading or writing. Memory bandwidth, the reading and writing part, is also calibrated in bytes per second at a certain energy per byte, and so is the transfer of data between chips. Over the last 10 years, which I might characterize as the first AI decade, we have seen something like a 300x performance in the flops per second that are deployable for AI by a typical graphics processor, a GPU. I think Jensen Huang has advertised something like 1,000,000x, but that includes another 3,000x from using 3,000 times more chips. So I'm talking about specifically one chip has moved by about 300x. I'm comparing the NVIDIA Maxwell generation in 2014 using 32-bit floating point arithmetic with the latest Hopper at about 2 petaflops of 8-bit floating point arithmetic in 2023, this year. Where has this improvement come from? Well, I've tried to break it down here. These are multiplicative factors, by the way, so they all multiply up to 300. Approximately half, or root 300, has come from using matrix multipliers on smaller number formats. In other words, going from float 32 to float 8. Much of the rest has come from improvements in silicon engineering, roughly an 8x improvement in transistor density over that time from 28 nanometers down to 5 nanometers. A little bit, 1.7x, has come from clock speed increase up to 1.85 gigahertz from 1.05, I think. But that has been expensive in terms of power. The power cost has been roughly a tripling of the power of the chip. And finally, a very small amount has come from improvements in the architecture of GPUs. I think this is because GPUs are well established in the graphics space. It was difficult to evolve those chips for AI without breaking their utility in graphics. Now, I think the AI market is large enough for the two chip types to have separated, and we will now see, I think, more architectural innovation. Obviously, my company is attempting to innovate architecturally as well. One thing I'm often asked is how large a die area does it take to build a petaflop per second of floating point units and the register files they need in order to be able to interact with the local memory. And this graphic shows you the large box, 32 by 25.7 square millimeter, is the biggest chip area that anyone can make in any fab in the world. The entire chip ecosystem is tailored to this maximum chip size. All the stepping machines, all of the wafer handling machines, all of the mask making machines make chips of this size. It may seem like a bizarre size, but that's what it is. And it will be a very, very, very long time if it ever changes or gets larger. So nobody can make a chip larger than about 823 square millimeters in any process technology. Of that chip, about a quarter is required to implement 1 petaflop per second of floating point 16 arithmetic units with small register files, and also to be simultaneously able to, do as an alternative mode, 8-bit floating point arithmetic, which is increasingly useful. And this is assuming they run at 1.85 gigahertz and they're in a 5 nanometer process, which is roughly where Hopper is today. It's also where our latest generation is today in terms of speed. The bad news is that transistor density isn't really going to get any better. So these points on this chart that show normalized density against year of approximate mass production are all real points. I have been responsible for every single, well, for a processor tape out in every single one of these processes at every one of those points. So these are real. This is not a marketing slide. Apart from the last two on the right. The last full point on the right is 3 nanometers. The one beyond that is the current expectation of 2 nanometers. And as you can see, I have drawn 2 lines One is for logic. Logic transistors come in pairs, one N-type, one P-type, hence complementary MOS. And SRAM cells, the static memory cells on the chip, it takes 6 transistors to store 1 bit. So generally, chip designers think in terms of pairs of logic transistors and sets of 6 SRAM transistors. And you can see that SRAMs stopped getting any denser in the last process node, 5 nanometers. In fact, 3 nanometers is slightly less dense, 2 nanometers roughly the same. Logic is slightly extending its ability to shrink, but only by depopulating the fins of the transistors. This makes the transistors weaker, makes them less controllable. It is possible they might go down to 1 fin, so there may be 1 further depopulation step. But you can see the general trend is the same as for the memory. In other words, a flattening, a dramatic flattening of the density improvement of transistors. No more transistors per square millimeter. So we've had 2000x increase in transistors per square millimeter over the last 25 years, and now that's ended. There is ongoing effort, of course, to improve transistor density, and there will be further improvements, but they will be slow, and crucially, they will not improve the cost per transistor. Here I've listed 3 things which are on the IMEC and TSMC roadmap. At 2 nanometers, we will see so-called nanosheet field effect transistors. And in this technology, the vertical fins are replaced with horizontal fin-like structures placed on top of each other. This allows transistors to operate at lower voltage, so it gives us an energy improvement, but doesn't give us any density improvement. Simultaneously, at 2 nanometers, TSMC have announced that they intend to implement buried power rails. This is a very sophisticated technology involving bonding wafers together, etching silicon vias through wafers, and forming metal underneath the transistors of one of the wafers. And all of that heroism, which allows the metal routing that delivers power to the transistors to be on the opposite side of the wafer to the signal routing, thereby saving space, only delivers 15% net density. This is a TSMC estimate. This will be in XPUs. I use the term XPU here to mean GPUs, TPUs, IPUs, any form of arithmetic accelerator for AI. It will be in XPUs in 2026, probably, but it will only deliver a 15% net density improvement. The next major step is 10 years away. And in this step, which is even more dramatic from a process engineering point of view, the N and P transistors are formed on top of each other, again to improve density, this time by perhaps an extra 50%. But it's 10 years away, so you can see the message. So what's happening? Well, people still want to build more sophisticated single nodes. So increasingly, you will see the combination of silicon die into larger assemblies. So in other words, innovation in silicon packaging. Packaging sounds like a boring term, but some of this is really very interesting and very difficult. I've shown some examples here on the top right, very briefly, 2 large die mounted on silicon interposers with HBM memory stacks, which are then connected to each other by a buried bridge inside the package substrate. That's the AMD graphics chip. In the center at the top is Intel's Ponte Vecchio, possibly the most ambitious, but also by far the most expensive construction of a GPU so far. 42 separate silicon die on 2 large silicon interposers on a substrate. On the right is something more modest and yet economically very significant. In Apple's laptop processors and desktop processors, they have mounted LPDDR pre-packaged memories onto onto an organic substrate that it shares with the bare silicon die. This is interesting because normally those memories would be mounted on a PCB. Mounting them on a substrate allows a far higher bandwidth to a memory technology it's not normally associated with bandwidth. I'll come back to that later. Bottom left, AMD's latest chips, in fact, beyond the Milan X now, use a technology called chip on wafer to mount an L2 cache piece of silicon on top of the processor cores. Those cores are then arranged on a substrate around an IO die into quite a sophisticated assembly. One of the most ambitious things done so far is the bottom center, Tesla's D100. This is a reconstituted wafer. In other words, a wafer of chips is formed, the wafer is sawn into chips, the working chips are identified, and then the wafer is reconstructed in a sort of plastic material out of the good chips. And that wafer then acts like a silicon wafer in that you can then metallize over the top of that. You can also do other things like attach soldered I/O connection directly to that reconstituted wafer. This technology has been in your mobile phones at the scale of about a square centimeter for many, many years. But this is the first time it's ever done at the scale of 30 centimeters across. And then finally, on the bottom right, our own chip. This is the first wafer-on-wafer vertical assembly. In other words, silicon chips placed on top of each other at the wafer scale before they are sawn. The reason why this is very interesting is because the pitch of vertical interconnections is very, very much finer than the alternative chip-on-wafer technology on the bottom left. This allows enormous vertical bandwidth, tens of terabytes per second at least, possibly hundreds of terabytes per second, to pass between the chips in a vertical stack. And this obviously allows you to build something that acts like a bigger silicon chip. So the other side of the evolution of silicon is the evolution of the performance per watt, the energy component. Again, these are the same points as I showed on the density slide. We've all heard of the end of Dennard scaling at 90 nanometers. This is the point at which the energy scaling that had been enjoyed in much of the silicon scaling era suddenly came to a halt. We went from roughly a 66% performance improvement per year in the operations per joule to about 18%. We are now in the third era, where there will be somewhat less than 10% per year from now on. I've characterized this as the constant voltage era. It's not quite constant, but it is almost constant. So you see the same characteristic. In other words, not only will we not get many more transistors in a silicon chip, but also the energy per function will not improve by much either. It will improve, but not by much. How economically significant is energy at a systems level? Obviously, it's environmentally significant. We're all trying to build the lowest power consuming computers we can, but is it a big deal economically? Here I show a rough breakdown for a very large scale computer installation, the sort of thing a hyperscaler might build. Roughly 2/3 of the cost is the chassis capital equipment amortized over time, perhaps over 3 years. So computers, switches, things like that. Only about 10% of the cost is consumed electricity, the third bullet. That can be as high as 15 or even 20% in a geography that has expensive electricity, but in most geographies it's only about 10%. However, there is another component, which is 15 to 20%, which is the cost of infrastructure that varies when you change the power. So there's a lot of infrastructure in a large-scale computer system to do with supplying the electrical energy and removing the heat. And this affects fundamental things like how big the hall of a data center needs to be. In other words, the physical costs of the building are a function of the amount of heat that must be removed. So if you add together that power component, in other words, infrastructure that's proportional to the provisioned power, if you add that to the actually consumed power, then you can see that roughly 1/3 of the cost of running a big AI computer is proportional to the energy component. So it is significant. It's about half as significant as the capital cost of making the equipment. Where are we today? Well, many of you will be familiar with this. The current generation of deployed AI systems consume about 3 picojoules per real flop delivered for training a large model on a big on a big machine. Something like a language model in transformer form on a hyperscaler machine would take about 3 picojoules per flop. So that means today, if we have 1 billion parameters and we train on 20 billion tokens, roughly the chinchilla point, then we might need 100 kilowatts for an hour, which is maybe 250 chips. If we scale that by a factor of 1,000 and scale the tokens by a factor of 1,000 correspondingly, Then we go up to 25,000 chips, 10 megawatts for 1 year, which is why nobody deploys trillion parameter dense models today. It's simply too expensive. There are trillion parameter sparse models. I'm aware of BAAI having done one of those, but not dense models. So we're sort of at the size limit of practicality today. And as I've said, it's not going to get much better for dense models. Why can't we just run the XPUs faster? Why don't we increase the clock rate? Many of you may know that CPUs, for example, often run at 3 or 4 gigahertz, but GPUs and IPUs only run at a bit less than 2 gigahertz, and Google's TPU only runs a little bit higher than 1 gigahertz. You can get silicon transistors to run rather faster than they do today. And in the graph here, I've shown how the speed of the transistors varies in the last several process nodes with the operating voltage. You can see each process node gives you a steeper curve, gives you faster transistors, steeper curve. The interesting thing is that they intersect. In other words, the point at which all of them don't operate at any frequency at all is not at 0 volts. It's at a threshold voltage, which is about 0.4 of a volt. So this means as you reduce the supply voltage of the chips towards 0.4 of a volt, the speed comes down very, very quickly, whereas the power only comes down in proportion to the square of that voltage. This gives you a curve of this shape if you plot the energy per operation against the operations per second. They're both normalized. And the small circle represents the point that that at least NVIDIA and GraphCore and some others have chosen to operate at. This is calibrated to a 7 or 5 nanometer process, and it's about 1.85 gigahertz at about 800 millivolts. Now, why have we chosen that point? Well, if you look, it is the point at which that curve becomes superlinear in operations per second. That means the power becomes super quadratic in performance, goes up very, very quickly. We could choose to run 20% faster at the cost of 40% more energy per operation. We don't, because that's quite expensive, but we could. We could choose to save power. We could run 40% slower and we would save 40% energy per operation. In future, perhaps we might do that in order to save energy. If energy becomes more expensive, we might do that. But the cost in performance is quite high and people are very keen to have as much performance as possible. So you can see there is a flexibility to change the speed at which XPUs operate. But it's a flexibility which is quite expensive. So that's why all the XPUs tend to run at about the same speed. Now, there is one thing we can do, and this is, again, a GraphCore innovation. We can at least make sure that the supply voltage is maximally used. A large silicon chip represents a very, very non-linear load to any power supply that's attempting to deliver power smoothly. Software can cause a chip to go from 0 activity to maximum activity in about 1 clock cycle, which is less than a nanosecond. And there is no power supply, or there was no power supply, able to keep up with that dramatic a demand for current. The very latest chips can switch hundreds of amps at a fraction of a volt in less than a nanosecond. No power supply could keep up with that. The innovation that GraphCore has delivered is to attach a second silicon wafer to the logic wafer. And that second silicon wafer is full of what we call deep trench capacitors. This is, if you like, a massive, very low impedance capacitor that is within microns of all of the transistors that are doing that switching. It's a very unique technology. It's formed by the same wafer-on-wafer technology as is used to connect the images to the logic processing chips in your mobile phone. So an innovative use of a pre-existing technology at a completely different scale, at the wafer scale. On the right, you can see the effect on the supply voltage. The upper trace is without this decoupling technology, and the lower trace is how well smoothed the supply voltage is once you attach this decoupling technology. And what this allows us to do is to not have so much headroom in our supply voltage. In other words, we can bring the average supply voltage down, and because energy of the chip is proportional to the square of supply voltage, because it's a capacitive technology, this brings the power down by quite a lot. In fact, we can get a 40% power saving without changing the logic die at all, or we can get a 40% speed up at the same power without changing the logic die at all. And you'll see from the earlier graphs I showed that that's like getting at least one whole process node, almost for free. It's very cheap to do this, by the way, cheaper than moving forward in a process node. So we can at least do that. Where does the power go? So this is a breakdown of the energy consumption of the processor tiles, all running a power virus on Graphcore's latest chip, the Colossus Mark IIX, we call it, with that wafer-on-wafer decoupler. It's a power virus, so this actually causes each flop to consume about 1 picojoule. It's worst-case data patterns applied to all of the tiles on the chip simultaneously. And that's at floating point 16. We also support floating point 8. You can see that most of the power does actually go into the floating point arithmetic. And most of the rest of the power goes into moving data about 1 millimeter, in fact, about 0.5 millimeter, from local memory to that floating point data path. In other words, there's not much power that isn't used for the work that we want to do. The bit in black that I've referred to as the no-op loop is the overhead of making a processor. In other words, we would have to have the blue and the orange parts, even if it was fixed function. So often I hear it claimed that if we built fixed hardware for a task like this, it would be much more efficient than building processors. This is not true. The programmatic wrapper of a modern processor, especially for this sort of application, is very lightweight indeed and costs very little in silicon transistors or in energy. So we are using the energy in the right places. What can we do? Well, we've already taken the precision of arithmetic down to as far as 8-bit floating point. There is now an IEEE standards group working on low precision arithmetic, and so far it has got to 8 bits. It will probably go on to 4 bits. The graphs on the right show on the horizontal axis how wide a range of scales one can get training of a transformer to converge with these 2 different types of 8-bit floating point format that are currently proposed by IEEE. One, it has 4 exponent bits and 3 mantissa bits, and one has 5 exponent bits and 2 mantissa bits. NVIDIA have very similar, but not exactly the same number of formats in their latest chips. You can probably see, if you stare at it for long enough, that for weights and activations, the upper format works very well. It works as well as 32-bit floating point. And for gradients of both types, the lower format also works as well, or at least in some cases better than 32-bit floating point. So 8-bit arithmetic works well. It saves a lot of power. What about 4-bit arithmetic? Well, there's been some recent work exploring the scaling laws of arithmetic. I refer you to this paper by Beth Detmers and Zettelmeier in particular. It looks like 4 bits of number codes might be the limit of precision scaling for inference going forwards. This is great. It means we can go further in terms of that improvement curve. We can deliver floating point 4-bit arithmetic with a map mile energy of probably half that of 8-bit floating points. The accumulation path, which is rather higher precision, starts to become significant. So it's not just a question of the multipliers, which do shrink quite a lot, but the accumulation path as well. And the net effect is perhaps a factor of 2 in terms of floating point operations per second, where 4-bit can be used. The other interesting observation I'll make is that the synapses in at least some parts of your brain appear to have a resolution of about 4 bits, 4.5 bits. Absolutely fascinating paper here. which you can go and look up, that demonstrates this in the hippocampus of the human brain. 26 resolvable levels distributed logarithmically over a range to make them look rather like 4-bit floating point. So if you believe that we're evolving towards brain-like structures, then that might be helpful. What happens to silicon over the next decade, given all that I have just told you? Well, I think, and I may be wrong, of course, it's very difficult to look forward 10 years in any technology that's moving fast. I think we may get 1.5 times as many transistors per die in 10 years. They will probably cost the same per transistor. We will probably manage to get a 2x improvement in the energy per operation at the same precision. And if we are able to go to 4-bit floating point, that will give us another factor of 2. So perhaps a factor of 4 altogether in the performance per watt. And we will see a lot of innovation at the multi-die architecture level. As the chips slow down, the packaging innovation ramps up. There are some people who do not share my prognosis. In particular, the US government does not share my prognosis. These are the targets set out by the US Department of Energy for proposals for their ACE supercomputer program for 2030. There are 2 machines to be delivered, one in 26, one in 2030, but these are the improvements expected by 2030. This is 7 years away. They are looking for a 140x improvement in performance and a 50x improvement in energy efficiency. I think I can say with the total confidence of a processor designer that neither of these things will be achieved. Let's move on to something that isn't in the processor, and that's the memory chips, which are increasingly important next to the processor. Today, most AI processors use HBM, high bandwidth memory. This is a vertically integrated stack of DRAM die sat on top of a controller die, which is then placed on top of a silicon interposer shared with the XPU, which is then placed on a package substrate, which is then placed on a PCB. It's a complicated structure. I'll come to that in a minute. There is a rival technology which is starting to emerge. And this is the memory technology that's used in your mobile phone. It's used in laptops. And it is starting to be used in much more high performance computing settings. This is called low power DDR. Double data rate, that stands for. It's a historical name that's not very helpful. This is also a vertically stacked technology, but using very much cheaper method. You will see I've highlighted on the right-hand side the difference in cost per gigabyte between these 2 technologies. They use exactly the same DRAM technology. They're built in exactly the same fabs by the same people, and yet there is a 7x difference in the cost per gigabyte of the final product. The reason for that is the complexity of the HBM. That may come down as HBM volume goes up, but probably will not come down to less than a factor of 4 difference, so it's still very low. The other differences between these technologies I've highlighted also in yellow. The first is that LPDDR allows much more memory to be connected to one XPU, about half a terabyte. But the rate at which it can be read, in terabytes per second, is only half as fast. This means that if you wish to read the whole of that memory, it will take you about 10 times as long as reading the whole of the smaller HBM memory. This is particularly relevant to AI because often that's what we want to do. In training, we tend to read and write the entire memory every iteration. In autoregressive token-wise inference, currently popular for the biggest language models, we tend to read the entire model for each generated token. And we generate the size of the model is generally dominated by the size of the memory is dominated by that. So we are reading the whole memory on every cycle. So the cycle time is very important. And HBM certainly wins in cycle time. However, it loses in capacity and it loses in cost. I think we will see both of these memory technologies having a role to play in AI processing. And I think NVIDIA agree with me because if you look at the Grace Hopper device, HBM is attached to the GPU part of that, and LPDDR is attached to the CPU part of that. So maybe that's the best situation, have a lot of both, but obviously that's a very expensive situation. So I think we'll see chips that have one or the other, as well as both. In an AI context, memory you can't cycle through or touch in less than a second really isn't very useful. And let me give you two examples of why that is the case. SGD training, which I've drawn here, the red parts are forward path and the black parts are the formation of gradients on the backward path. SGD training, as we all know, is a first order optimization mechanism, requires a lot of iterations, typically of order 1 million iterations. So if we're prepared to wait a few weeks to train a model, then we do need to do each iteration in a few seconds. Each iteration reads and writes all of the memory. Therefore, the memory has to be cyclable or touchable in less than a second. Or in other words, the memory bandwidth needs to be about the same as the memory capacity. Gigabytes per second needs to be about the same as gigabytes. A second example is token-wise autoregressive generation. In this case, we want to read the full model and any cached KV values per iteration, and we want to do that many, many times per second. So we're reading the whole memory many times per second. That means, again, a memory which is so large or so slow that it takes more than a second to read is not very useful. For this reason, we won't see the class of memory that's used in servers being used in AI, for example, so-called DDR memory. It'll stay popular in servers for a while, but you won't see it in AI machines. You also won't see flash memory, things like NAND memory. It's very, very cheap, but unfortunately it wears out after a few thousand or even a few hundred read-write cycles. So if you built an AI machine and attempted to do a single training run of SGD, you'd get you wouldn't get very far into it before your memory was destroyed. We can put quite a lot of static memory, in other words, logic transistor-based memory, on a full reticle die alongside those flops. This is something in particular that the Graphical's Colossus IPU does. About half of the die area, in fact, is covered with static memory, SRAM. This is a die shot, and you can see I've highlighted one of the nearly 1,500 processors there. Each processor has 624 kilobytes. So in total, we've got about 900 megabytes of SRAM on this chip. And there's quite a lot of bandwidth between chips. So over a cluster, you've got a few gigabytes of SRAM. If your model is of order 1 billion parameters or fewer, then you don't need an external DRAM at all. And in fact, this was the design basis for this chip. This chip is designed for situations where you can fit the model in the chip itself or across a cluster of chips connected together. When you can do that, then you can access the memory about 10 times faster than even HBM. You can access it at many tens of terabytes per second. In the case of this chip, 65 terabytes per second, a speed completely unachievable with any dynamic memory. So that's an option, at least for modest models. There is another situation in which having a lot of SRAM on the chip is very useful, and that's the second bullet here. If you have a large model, such that you do need external DRAM, then it is still very useful to have enough SRAM on the chip that you can read each matrix from DRAM only once each time you do a forward or backward pass through the model. Many of today's chips do not have that amount of SRAM and have to read parts of the model more than once to do a forward pass, for example. Why is it a good idea to only read it once? Well, because accessing data from external memory is expensive in terms of DRAM energy, and also bandwidth to DRAM is limited. So if you can read it once, if you've got enough SRAM to read it once, that's an advantage. Finally, the other resource that we haven't spoken about is inter-chip links. How much inter-chip bandwidth can we fit on a chip? Well, if we've used up the long edges for memory for external DRAM using either HBM or LPDDR, then we have the short edges, what chip designers call north and south, in which to fit chip-to-chip links. This is what's normally done. We can, with today's technology, fit about 128 100 gigabit so-called SerDes lanes. SerDes stands for serialized, deserialized. It's just a 1-bit wide lane technology that supports 100 gigabits per second in each direction. This is what's used for 100 gigabit Ethernet. So think of it as 128 100 gigabit Ethernet lanes. That gives us 1.6 terabytes per second, full duplex, in other words, in both directions simultaneously between chips. The cost in power is about 60 watts per terabyte per second of capacity. So if you implement the full capacity, about 100 watts. And unlike RAM, unlike DRAM, SerDes consume power all the time. So even if you're not sending anything, they're still consuming 100 watts. Whereas RAMs only burn power when you actually send data. 100 gigabit lanes don't reach very far. They will reach about 30 centimeters in a PCB, or about 2 meters in a well-designed copper cable. So they are sort of in chassis or at most in rack technologies in copper. If you want to go further than that, if you want to go between racks, then you have to use optical transceivers, and that roughly quadruples the power cost. It also quadruples the dollar cost. So it's a very, very expensive thing to build optics. However, there is huge demand for increased bandwidth. So we will see more optics. We'll see optical transceivers going onto the board next to the chip. Eventually, we'll see optical fibers going to the XPU itself, but not for many years yet. How much bandwidth do I actually need? Do I need to put all that bandwidth on the chip? Well, here's an example. You can formulate many examples, but if we take float 16, we do 1 million training iterations on a big model, and we distribute the optimizer over the model. Then for each iteration, we need to do a collective, which consists of reduced scattering weights, doing a local update on a subset of the weights, and then all gathering the weights. It's one all reduce operation comprised of a reduce scatter operation and an all gather operation. To do that, the links have to transfer 4 times the number of model parameters in terms of data reads. In terms of data. And that is also the amount of data, model data, that must be read from the DRAM by the local processors per replica, per iteration. Meanwhile, the total training flops is about 6 flops per parameter per token. And if we use the usual metric of 15 to 20 times as many tokens as parameters, then it's about 100 model parameters squared. And I've shown you some examples here. So for 100 billion parameters, if we were to use 256 model replicas, which is reasonable, then about 10,000 flops per byte. And that's per byte of both the memory access bandwidth and also the interchip transfer bandwidth. It's interesting, for training, you need about the same amount of bandwidth for each. About the same amount of bandwidth between chips as you do to the memory, if you minimize the memory bandwidth by having enough SRAM. For 10 billion parameter models, you wouldn't need as many replicas, and the number of flops per byte goes up, but not by very much. So you're talking roughly 10 to the 4 flops per byte for the transfer operation to take the same amount of time as the flops. You probably want the transfer collective to take less time than the flops. So a petaflop chip that perhaps delivers 50% of those flops in anger would require at least 100 gigabytes per second of memory bandwidth and at least 100 gigabytes per second of transfer bandwidth. Perhaps more if you could fit, but probably not terabytes per second, which is interesting. Because GPUs in particular are sold today on the basis of their bandwidth being useful for training. It's not really used by training. Training is still totally flop dominated. The same is true of many types of inference. So a training machine does not need multi-terabyte per second DRAM. It also does not need multi-terabyte per second inter-chip connectivity, but it does need at least hundreds of gigabytes per second for both of those. Let's look at a situation where we really do need a lot of memory bandwidth, and that, of course, is token-wise auto-regressive generation. This picture is a cartoon of one layer of a transformer stack. The section on the left is the attention part. The section on the right is the feed forward network part. The red objects are weight matrices. The black plain objects are activation matrices. And because it's token-wise autoregressive, only one token in each of those activation matrices is active on each iteration, except for the cached history of K and V that I've highlighted in light blue. I've used the notation that D is a dimension and Q is the context length for these things. And if you look at the number of flops per value read from memory, then you come up with this equation. And notice the batch term in there. In other words, the equation allows you to batch up more than one conversation in order to try and get better flops per read. This is quite commonly done. Without that, the arithmetic intensity of autoregressive token-wise generation is just 2 flops per read. In other words, if you've got a 3 terabyte per second state-of-the-art HBM memory system, you are only going to be able to use a similar number of teraflops per second, not the petaflop per second that the chip is capable of. If the context is small, then batching helps up to a point. We can get towards an asymptote of 12 times dimension over context. If the dimension, for example, is 8,000 and the context is 2,000 tokens, then that's maybe 100 flops per byte. You're still going to be totally DRAM bandwidth limited on a modern GPU or similar. For large context, which of course increasingly is what we want, there's an explosion of research into how to get large context to work, then batching cannot improve the computational intensity at all. In other words, you are stuck at 2 flops per read. And I've highlighted in red the killer statement. If this is the universal model for deployed AI, token-wise autoregressive inference, which is the case today, and if we want a large cache history, so that these models don't forget what you were talking about 10 minutes ago, then we don't need XPUs. None of the current arithmetic accelerated chips is suitably designed for this constraint. What we should build are chips with a lot of memory bandwidth and not many flops at all. And they would be much cheaper and they would burn much less power. In other words, we've suddenly got a massive mismatch between the expensive chips we've built and the algorithms which are currently the most valuable to us. What can we do about it? Well, we could build different chips. If the algorithms don't evolve, that's what will happen. It will take time because new chip generations take several years, but that's what will happen. And those chips will maximize memory bandwidth and they won't have much arithmetic. Algorithmically, there are other alternatives. We can compress the history term that prevents batching from working so well. We can sparsely access the history term, has the same effect, we fetch less history. We can do a hierarchical form of autoregression using sort of super tokens and then generating tokens within those super tokens. And that reduces the iteration rate for much of the model, for example. We can perhaps not use autoregression. So not all generative AI uses autoregression. The image generators, for example, Mid-Journey, Stable Diffusion, they're not autoregressive per se, they're iterative, but they iterate over the whole image, the whole data sample, not over the token within the data sample. And this means they have a much higher flops per byte. Arithmetic intensity makes them act much more like training. In other words, they're very suitable for a flop-centric chip with high memory bandwidth, but one that's more limited by flops. So perhaps language will yield to iterative diffusion denoising instead of autoregression. Or perhaps language is intrinsically better with autoregression and image is intrinsically better with diffusion denoising. Who knows? We are discovering that at the moment. Other things we can do, we can partially model all of the information we wish to be available to the AI and not model other parts. And I'm particularly attracted by this idea of separation of concerns, because I think it's something that both the algorithms and the hardware can play with. So what is learned by a foundation model that we train? The first thing we learn, of course, is the ability to communicate, to use a language, to form well-constructed grammar, to be expressive, to be fluent. In multimodal models, we may use other media like pictures. So fluent communication is learned by a large foundation model. We also learn a lot of knowledge about the world. And finally, we learn how to do some reasoning, at least common sense reasoning, or you might characterize that as computation. The ability to construct and execute algorithms emerges with scale of large foundation models. Now, these three things are separate to some extent, surely, much like a human is separable from a knowledge base like Wikipedia and an algorithm execution engine like Python. Perhaps humans have to do that, of course, because we have limited brain capacity. Perhaps AIs don't have to do that, but it might be efficient if they did do that, separate concerns. Then the autoregressive part would probably, if it was token-wise anyway, only have to deal with the construction of language. And that part of the model could be very much smaller than the bulk of the model. This is one example which I'm sure you're all familiar with, the idea of retrieving some information in a large language model. In other words, query comes in, there is a first network that performs an analysis on the query and constructs a retrieval, well, command almost. The retrieval command goes to a database of knowledge, which is not modeled, it's indexed. In other words, it's been organized so that we can retrieve relevant things, but it's not actually part of the parameters of an autoregressive model. That indexed but unmodeled data is then fed into a third network, which together with the query synthesizes a response. In other words, we separate the knowledge state from the language, from the state necessary to be good at language. And the knowledge state, this allows the knowledge state to be very, very much larger than the iterative part of the model, at least the token-wise iterative part of the model. It also allows us to deal with issues like currency of the model. In other words, we can add data very quickly to that knowledge base and it's immediately available. We can also derive attribution. We can ask the model for references that it has used to provide the response. So this separation of concerns characterized by retrieval networks, I find very attractive. And it certainly helps to solve that mismatch between chips and algorithms. So my conclusion is that there will be no universal XPU, where an XPU is a GPU, an IPU, a TPU, whatever you want to call it. A machine well designed for training or for parallel inference, like image generation, will maximize flop rate. In other words, it will have a very high arithmetic intensity. An autoregressive generation machine that operates on small quanta, like tokens, language tokens, will prioritize memory bandwidth. It will have a low arithmetic intensity. You cannot design an efficient chip for both high and low arithmetic intensity. You need two different chips. And finally, a compact stamp for large model inference or for fine tuning prioritizes memory capacity over either flops per second or gigabytes per second. It's a question of how many gigabytes can I have? Can I fit my GPT-3 model on one chip? This will be possible with LPDDR memory. And again, that implies a different sort of chip design to the previous two. So there will be a diversity of XPU machines, and we will learn to use all of them because there is a diversity of AI requirements, and AI is sufficiently valuable to justify more than one chip architecture. There will be no universal XPU. Finally, this is my last slide. I like to think of the evolution of AI algorithms as having been through two steps to get to where we are, almost where we are today. Initially, we discovered that if we built deep neural network structures, we could learn from data in a surprisingly good way. This learning was supervised and data was therefore expensive, so our ability to scale models was limited by the cost of data. We then learned how to use unsupervised learning, so data became cheap. We could use the internet. We had to do some filtering of it, but basically there was a lot of cheap data. That's when models exploded by a factor of 1,000, and we have today's language models, for example, or multimodal models of order 100 billion parameters instead of the ResNet era image models of order 100 million parameters. So 1,000x increase in scale. If we now harness the ability to access state sparsely, then there is the opportunity to go further and then to be limited by the cost of memory. And the comment at top left is a sort of truism of all computer design. And that is that what can be computed is a function of how much memory you have. The number of flops per second and the rate at which you can access that memory determines how fast you can compute. But the amount of state that you have in your system determines what can be computed. So ultimately, the intelligence of any agent is limited by the information available. In other words, by the memory capacity, not by the flops per second, not by the gigabytes per second. So I think there will be a pressure towards memory capacity as well as the other parameters to do with speed. That is all. Thank you very much for listening. Oh, I can't hear you.
Okay.
Thomas. I can
now.
now.
It works. It works now. Yeah. Thanks, Simon. Okay. Thanks for you. Thanks for giving us such very informative report on talking about how silicon could form chipsets and could form XPUs that runs very smart AI algorithms. So on basis of what you present to us, I have some kind of a couple of questions. As you just mentioned in the last, there's no general or there's no universal XPUs. So does it to say, or is that to say, there's no what can I say? So is that to say, there's no what can I? There's no single one XPU or architecture could enable the optimization of various AI algorithms. So can we say that there's no one single XPU architecture could enable the optimization of various AI algorithms?
Yes, that's very much what I'm saying. So I remember when multimedia emerged as a computer workload. So the processing of images and video and sound, this was in the early 1990s. And all of the CPU vendors at the time said, you don't need new chips for this. We can do this on CPUs. And of course, CPUs are general purpose computing engines, so you can do anything on them. However, it's not efficient to do that. And so we saw the emergence of media processors, types of signal processors, which are now everywhere. So your mobile phone, your laptop, they all have media processors embedded in them. And it always comes down to that question. There will be chips which are purpose specific for any market that's large enough to justify the expense of producing them and has sufficient volume. AI, obviously, is a very, very broad technology. It will be used in many, many ways. It will affect probably every business on Earth. And we already know that there are a variety of different models and different modalities like training, operating modalities like training versus fine-tuning versus inference that all have different requirements. They're all going to be very, very large-scale workloads. So it will be worth developing architectures for each of these things. I also think CPUs have a role to play in AI, especially as they develop higher bandwidth memories. they might well support that middle bullet. In other words, we might find that we're doing inference on our autoregressive language models in a few years' time, not on a GPU, but on a CPU. But GPUs will still exist, and IPUs will still exist, and TPUs will still exist, and DSPs and media processors and everything else will still exist. There is today a very rich diversity of types of processor chip, and AI will increase that diversity. It won't be all GPUs for AI.
Yeah, okay, thank you. So next question is about IPUs. You know, and everyone knows then that you are one of the major chief architects of the IPUs. So what are those kind of the some of the challenges you faced in encouraging the adoption of IPUs over more established technologies like GPUs? Yeah.
That's a very good question. So for a new company to emerge successfully, I think there are two fundamental requirements, at least in the chip space. This is my career experience. First of all, you need a new market that provides new opportunities, a market that's not already owned by somebody. And AI represents that sort of market, a market suitable for new chips, which is sufficiently big. And the second thing you need is that if there are large players who are moving into that market at the same time as you, and in our case, a large player might be NVIDIA, then you need to do something different to what they're doing. And I was surprised at how many of startups that started to address AI essentially attempted to clone what NVIDIA was doing, make a GPU. I don't see the utility in that, and I don't think it's a successful business plan, because the enemy will always have advantages of scale and incumbency. So you have to do something different. So the challenge for us was to build a different type of architecture that did not look like a GPU, but which was still very useful for at least some parts of the AI computing space. And characteristics of the IPU that distinguish it from GPUs include, for example, the enormous amount of on-chip SRAM, so that medium-sized models can be fitted on the chip without any DRAM at all. And that gives you tremendous performance, tremendous power efficiency. That's one thing. Another characteristic of IPUs that's quite different from GPUs is that IPU consists of a very large number of completely independent processors. In other words, its parallelism is much more at the program level, the sub-program level, and not at the data path level. Much of the parallelism in a GPU derives from vector operations or vector data paths. IPUs do have vector data paths, but they are small relative to GPUs, and you have many more independent sub-programs. This means that if your data structure is less regular, like, for example, a graph neural network, then an IPU has a great advantage. And we have shown, for example, we submitted our first attempt at the OGBLSC, the Open Graph Benchmark Large Scale Challenge last year. We made our first submission and we came top in the 2 out of 3 categories that we entered. At our first arrival, we beat all other technologies in that area. And that is a testament to the fact that IPUs are very, very good for graph structured data, such as molecules, such as knowledge graphs, for example, representing knowledge bases.
Okay, that'd be great. Sure. So one last question. So it's about the whole market. It seems now in the there are a bunch of this kind of the large language models in the world now. So it is estimated that the demand of the computing power, I mean the demand of the computing power will probably just get an extraordinary growth by taking a long view, probably in the coming 5 to 10 years. So how do you estimate the overall demand scale and the growth rate of computing power by taking a long view, things are sort of like by 2030, how do you estimate the overall demand scale of the computing power and how it grows?
I think it's probably impossible to estimate because of the profound nature of the AI breakout. I think that the emergence of AI is the biggest technological step that humanity has made since the harnessing of machine power, at least, in other words, since the invention of engines. And much as the inventor of steam engines would have struggled to tell you what was going to happen 10 years later, I struggle to tell you what's going to happen in artificial intelligence machinery in 10 years' time. It is obvious to me, at least, that all computing will have elements of learning from data. So if AI is characterized as learning from data, then all future computing is AI to some extent. It's also obvious that AI provides the opportunity for using computing in many, many areas where computing wasn't previously used. In other words, the size of the computing market will go up dramatically. So it will all be AI, and it will be bigger than it is today. Let me give you an example of one area. This is not an area that GraphQL is particularly focused on, but and it's currently a little bit out of fashion, and that is autonomous or semi-autonomous driving. The number of cars sold every year is currently about 10 times as large as the number of server computers sold every year. So if a car becomes a powerful server computer in order to provide semi-autonomy or autonomy, then suddenly your computing market has gone up by a factor of 10. That's just one application, one type of technology. I think there'll be many, many of those applications. So it'll be enormous. And this is why energy efficiency is such a big deal. I'm not an alarmist in terms of the amount of energy currently used by infrastructure computing, but there is the possibility that that amount of energy will go up by a factor of 100. And if that happens, I will be alarmed.
Oh, that'd be great. Okay, thanks, Simon. Okay, thanks. Okay, it's really my honor to host this session and with you. And I just noticed that GraphQL has office in Shanghai, so probably, and then we can. I'm really looking forward to meeting with you offline, probably in your Shanghai office next time. I still have a lot of questions, burning question to raise. Yes, about how computing power and how what's the very magical relationship between the AI algorithm or the software part and the hardware part of the chip design. Okay, thank you. Thanks for your time, Simon. Thank you. Bye.
Thank you, Jones. Thank you. Goodbye.